Well, a funny thing happened yesterday afternoon. I was sitting at home grading, decided to check YouTube, my YouTube channel, and see what was going on. And well, something amazing went on. The video of the last 5 minutes from Friday's class had a little mini viral moment, or a little mini 3-hour moment. I don't know if you can see this very well. You can see it's about the Riemann hypothesis. It's got over 1,300 views right now. And between like 3 o'clock and 8 o'clock last night, it had over 1,000. That's never happened to me before. I had 1,300 videos or so total. And that was the first time that ever happened. There you can see its graph. So that was kind of wild. I didn't know quite what to expect. You know, the Riemann hypothesis is a very famous thing. So maybe in that sense, it's not surprising. So got some interesting comments too. This one's kind of funny here. Let's turn off the volume though. Ignore the commercial. I like this one here. How'd this end up on my recommendation? And how would YouTube know that I would enjoy it? One of the responses for me, I'm just glad that you enjoyed it. Gave him a couple other videos. So anyway, it was a very interesting moment. 1,300 videos, that's the first time it's happened. I have a fair number of videos that have over 10,000 views, but they typically take a while to get there, build up over time. So it was very strange for that to happen in the very first day. Thank you for those of you who are online. I hope you enjoyed today's video as well. I'm going to start with some interesting animations to motivate where we're going with things here in this class. The main content of today is kind of dry. It's about series tests for convergence and divergence, and there's lots of tests, and it's difficult to focus, but let's get ourselves motivated by thinking about where we're going. Where we're going is what's called Taylor series in chapter 10, and Taylor series are actually really cool. And here I've got some animations that illustrate how Taylor series work. This example, the red graph that you see is the graph of 1 over 1 minus x. And the blue graph, well, the starting blue graph that you see here is just y equals 1. What I'm going to do is play this animation, and we're going to see the blue graph get closer and closer to the red graph. Let me actually slow it down so you see each individual graph. Kind of like a dog wagging its tail over there. The blue graph gets closer and closer to the red graph, but only on a certain finite interval, it seems like. Just from -1 to 1. By the way, that red vertical line is just the vertical asymptote. You can ignore it. Why is it doing that? What this is illustrating is the fact that this geometric series (1 plus x squared plus x cubed plus x to the 4th, etc., forever and ever. That is a geometric series whose first term a is 1 and whose common ratio is what? X. It's got to converge to a over 1 minus x, which is 1 over 1 minus x, if the absolute value of x is less than 1. We've already talked about geometric series. In other words, by the way, you should always think about what this means in terms of the number line. If the absolute value of x is less than 1, that also means x is strictly between -1 and +1. When that's true about x, you can say these two things are equal. Now remember, this is all convenient fiction. When I write an infinite series, I'm only pretending to add up infinitely many terms, but I can make that rigorous in terms of partial sums. And I'm saying the partial sums of this converge to this thing as n goes to infinity. That's what's really going on. Okay. And what I'm seeing in the animation here essentially is partial sums from the left as the degree of the partial sums, which are polynomials, gets higher and higher. Again, when n is 1, it's really just 1, horizontal line, the blue line there. When n is, well, in this animation, when n goes from 0 to 1, then the line becomes 1 plus x, slope of 1 and a y-intercept of 1. The next term brings you to 1 plus x squared, which is a parabola. That blue graph there is a parabola. Then the next value then goes up to n to a cubic. That blue graph is a cubic. Then a 4th degree, then a 5th degree, then a 6th degree. And we see the blue graph approach the red graph when x is between -1 and 1. You might wonder, why can't it get past -1? What's holding it back? The reason has to do with imaginary numbers, and maybe I'll talk about it later, not today though. Why it can't get past -1. The deeper reason is because of imaginary numbers. You can do this for more than just 1 over x. You can also do it for, say, e to the x. There's e to the x. I'm going to enter these functions and make a similar animation. That red graph is e to the x. The blue graph happens to be the graph of 1 plus x. If I increase n by 1 step, I get a quadratic, a parabola. Increase n by 1 again, I get a cubic. Keep going. I can keep increasing n here as well. And once again, it's like it's wagging the dog tail there. However, at least if I let n go up large enough here, let me try 40 instead of 20. What you're going to see is the blue graph's tail wagging on the left side there doesn't seem to be limited by some boundary like -1 was in the previous example. It keeps getting better and better as it moves to the left as n increases. So what this is illustrating, not a proof, but what it's illustrating is the series, what's called the Taylor series for e to the x, turns out to converge to the red graph e to the x no matter what x is. Though you do need a larger value of n to get closer if x is further away from 0. Another example, here's the sine function, sine of x. That's the red graph. The blue graph is 1 plus x. Let n increase. Actually, I'm just jumping up to a cubic. We're only looking at odd powers here. Then a 5th degree, then a 7th degree. Now we see these polynomials, these Taylor polynomials, converge to the sine function as n gets larger, illustrating that in the limit, things are simpler. The Taylor series actually equals the sine function. For cosine, it's even more fun because then it's like a bird flapping its wings. Come on, there we go. Or I make it go faster, then it's like more like a bird flapping its wings. That's too fast. Oh, okay. It's not ideal, but it's kind of like a bird flapping its wings, you see. The Taylor polynomials are converging to, in this case, the cosine function. And the convergence is fast when x is close to 0, slower when x is far away. But no matter what x is, if n is large enough, you're going to get a good approximation. And in the limit, as n goes to infinity, you actually get equality. Now, you might wonder, why do we care? Why should we want a sine function or a cosine function to equal some series? The answer is pretty deep. Mathematically, it corresponds to making good approximations, and it is related to how calculators and computers are programmed. It's not exactly how they're programmed. You need something called interpolation as well. But it's related, okay? For science, it comes up in differential equations. Using Taylor series sometimes makes things simpler. Going to infinity often makes things simpler. If you take diffie-q and linear algebra with me next fall, you'll see that. Right? Take more physics and engineering courses, they sometimes do need to use these Taylor series. Anyway, we don't fully get to the topic of Taylor series until chapter 10. This is just a little preview. For the rest of the day today, we need to do some hard stuff. And again, it's not the most exciting stuff, but it is important. Series tests for convergence and divergence, and when should you use them? Okay. Now, what I'm going to show you here on some printouts, I did already put on Moodle, and you can certainly download the clean printout if you like it and print it out for yourself. It wouldn't probably be a bad idea to write some of these down anyway. They are in the textbook as well, though I've written them a little differently than the textbook. Okay. So, and I've added some comments too. So it's not necessarily a bad thing for you to write these down. The first thing you should use, always, you should think about this. Okay. Always, no matter what the series is, you should think about this thing called the divergence test, which, as the name implies, can only be used to prove divergence, never convergence. That's the first thing to realize. That's a comment worth writing down. Only use the divergence test to prove divergence, never convergence. However, another thing worth writing down is, in most interesting examples, the divergence test does not apply, can't be used, because the hypotheses are not satisfied. So even though it's the first thing you should think about in any given problem, typically you're not even going to be able to use it. It's only in lucky situations where the textbook author or me is testing, do you know about the divergence test? Would you use this? What does it say? Let's focus on the second sentence first. The second sentence says, I say, therefore, if the sequence of terms, the AKs, does not converge to 0, which means either the AKs, the terms, converge to some non-zero number, or the AKs diverge as a sequence, not a series, as a sequence, a list of numbers. The conclusion is then the series, emphasis on the word series with a summation sign. The summation sign must be there. This is where people get sloppy. When you're talking about the series, you have to put the summation sign. Otherwise, you're completely missing the point. And you don't want to miss the point. For one thing, you won't get as many points on the homework or test. But more importantly, you want to understand. We're talking about ultimately series, infinite sums. We're wondering if they converge or not. In this case, it diverges. We actually have already applied this last Friday. When we consider these examples, there was first of all, the example where we did 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 with summation notation. We let k go from 1 to infinity. We were adding up -1 to the k plus 1. And yeah, if you write that out, that's 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1, etc. The partial sums were 1, then 0, then 1, then 0, then 1, then 0, then 1, then 0. The sequence of partial sums did not converge, and therefore this series diverges. But you also can use the divergence test. In this case, AK is this thing here. That's A sub K. It does not go to 0 as K goes to infinity. Therefore, 3 dots means therefore, the series, emphasis on the word series, not sequence. The series, this whole thing, diverges by the divergence test. Again, on Friday, we proved it diverged because we just looked at the sequence of partial sums. Now we're proving it diverges using the divergence test. As another simple example from last Friday, summation k goes from 1 to infinity of 1. 1 plus 1 plus 1 plus 1 forever and ever. Now the AKs are all 1s. AK equals 1 for all k, which does not go to 0 as k goes to infinity. Therefore, the series diverges by the divergence test. This series here diverges. Use the word series there. If I was going to write the series again, I want to make sure to include the summation. Question? Right? That's a divergent sequence. If you got a sequence going back and forth between 1 and -1, it's not convergent.
I know, but if you look at the sum, that goes and it's larger, it flip-flops between 1 and 0.
Right? Which means it doesn't converge, it diverges. It's not approaching any particular number. Does that make sense?
I always thought divergent means.
Nope. It means it just divergence means it just does not converge, does not have a limit.
Okay.
So yeah, that's the answer. Next example, summation k goes from 1 to infinity of k over k plus 1. If people are not real familiar with series and they're just starting to learn about it like you are, you look at that and you might say, I have no idea if that converges or not. Certainly k over k plus 1, that term without the summation sign, those terms go to 1, right? Because it's a ratio, it's a rational function of k where the degree of the top and the bottom are the same. So the limit of that as k goes to infinity is the ratio of the coefficients of the highest powers, which are both 1. I didn't write them. This approaches 1 as k goes to infinity, but the series diverges because the terms don't approach 0. If you wrote this out without a summation sign, it would be 1/2 plus 2/3 plus 3/4 plus 4/5. You can clearly see those terms that are being added do not go to 0. They have a limit, ak goes to 1 as k goes to infinity, but 1 is not 0. Therefore, the series diverges once again by the divergence test. The series, the infinite sum, diverges. And I hope that's intuitive. Those numbers are getting closer and closer to 1. You're not adding up numbers that are getting smaller and smaller. The next thing you should ask, if the divergence test does not apply, which it usually does not, is our series geometric? Actually, in the case where it's a divergent geometric series, you could also apply the divergence test. Before we do look at the geometric series, one more comment here. Yes, this is a divergent series, but there's nothing stopping me from writing it. I did write it. And you're like, okay, well, big deal, you wrote it. This is once again highlighting the distinction between the series itself, which is just a mathematical expression, a summation sign with an expression there, an AK, or a bunch of numbers plus ... I can always write those things even if they diverge. But if they diverge, I should not say they equal anything. Though some people might say they equal infinity or something in this kind of example. But remember, for us, infinity is not a number. Here's another comment that's important, but kind of subtle. Divergent series actually are sometimes useful. Wait, how can that be? How can a series that does not converge be useful? One answer is that divergent series, even though they diverge, sometimes have partial sums that are good approximations, amazingly enough, for whatever you might want to approximate. Maybe the first and second partial sums are not so good, but the third, fourth, fifth, sixth are pretty good. But then once you get to the 7th, 8th, 9th, and 10th, they get bad again. That does happen, actually. The other reasons they're useful, in fact, I'll share, has anybody ever heard of Numberphile? 1, 2 people. Numberphile is another video channel on YouTube, a math channel. And they have a video where they talk about divergent series that generated a ton of controversy. If I remember correctly, they argued that 1 plus 2 plus 3 plus 4 plus 5 plus 6, etc., forever and ever equals -1/12. I'm serious. I'm not lying to you. That's a divergent series, but Numberphile argued it's -1/12. So are they just pulling your leg? Are they lying to you? Trying to mess with people's heads? Well, I think they were trying to mess with people's heads somewhat. But actually, even though officially speaking, this is divergent, so technically it doesn't equal negative 1/12. From a certain perspective in some applications, it does equal negative 1/12. But that other perspective is not the perspective that we take. That's the short answer. Weird, but true. I'll share it with you, but don't let it confuse you too much, okay? It's just treated as something kind of weird and fun. Okay, geometric series. We've seen these already for at least 3 class periods. Summation k goes from 1 to infinity of a times x to the k minus 1. That's the typical way we've written it with summation notation. And here we've written it the typical way we've written it long way with the plus dot 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 dots. First thing I want to do here is just emphasize this is not a unique way to write it with summation notation. Here I wrote it the same series with a different summation notation. Here I'm starting k equal at 1. Here I'm starting j at 0. First of all, it doesn't matter whether you use I, j, k, m, or n for your index of summation. That's irrelevant. Second thing that doesn't matter is where you start the value of k or j, as long as the pattern works, as long as it matches this long form. In either case, the first power of x with the leading term is x to the 0 power, which is 1. When k is 1 here, k minus 1 is 0. When j is 0 here, j is 0. It is the same series. In fact, you can even go from here to here thinking of it in terms of a substitution, like with integrals. Let j equal k minus 1. That would be the substitution to do. Don't do dj equals dk, though. There's no integrals here. Just do j equals k minus 1. We already know this converges if and only if its absolute value of the common ratio is less than 1, meaning it's between negative 1 and 1. Always remember that. Therefore, it diverges if and only if the absolute value of x is greater than or equal to 1, which means x itself is either less than or equal to negative 1 or greater than or equal to positive 1. We also have seen that when it does converge, when it converges to a over 1 minus x. And we write this equality as if we have literally added up infinitely many terms. Now remember, we really haven't added up infinitely many terms. We're just pretending. But it's a useful pretending, and it's a pretending that can be made rigorous by talking about limits of partial sums. Sometimes you're given a series that looks kind of geometric, perhaps you might say, in looking at it, but doesn't fit one of these 2 summation patterns. Here's an example. Let k go from, say, 3 to infinity of 5 times negative 5/6 to the, say, k minus 2 power. It doesn't fit any of these patterns, it seems, or either of these with the summation sign. However, it kind of does. I mean, you still have a number times another number to a certain power related to the index of summation. The quickest way to confirm this is geometric for you and to figure out what its sum equals if it converges is to write it out the long way with the plus dot dot dots. What's the first term? Plug in k equals 3. The first value of k, 5 times negative 5/6 to the 3 minus 2 power is 1 power. Next, increase k by 1 to 4, get 5 times negative 5/6 to the 4 minus 2 power, which is negative 5/6 squared. Then when k is 5, the next value of k, you'd have 5 minus 2 power, 3rd power, etc. Put the plus dot dot dots. This is geometric. To get from any term to the next term, I multiply by the same constant. What is it? What's the constant? Negative 5/6. A, the leading term is that, which is negative 25/6. And the common ratio, which we've called x, but some books call r, common ratio is negative 5/6. The absolute value of negative 5/6 is positive 5/6, which is less than 1. Therefore, the series converges. It's geometric with common ratio having an absolute value less than 1. What does it converge to? It converges to a over 1 minus x. Let me just say therefore converges. Series converges. A again is negative 25/6. X is negative 5/6. That's going to be negative 25/6 over positive 11/6. The 6's can cancel there. This simplifies to negative 25 over 11. Mathematica to help us believe that. Use the summation sign. That's the only way you really can do it in Mathematica. On the button on the palette there, k goes from 3 to infinity, make it infinity by doing escape high and escape. There's what the summation terms were. 5 times negative 5/6 to the k minus 2 power. Notice I started k at 3. Now, mathematics is not just for me to do. You can certainly do this to check your work sometimes. In this case, yes, confirming the answer is negative 25/11. Okay. Once again, like I mentioned about 5-10 minutes ago, with geometric series, if you were in the case where x is greater than or equal to 1 in absolute value, you actually could also prove divergence with the divergence test. Either way is okay. Hanging with me here? Get yourself warmed up. We got a lot more to do. Drink some coffee. Anybody got coffee? We've talked about the integral test already. And I have typos here that I fixed before I put it on Moodle. I want this a to be a 1 and this a to be a 1. I'm not stating this in the most general way possible. I actually could have allowed those lower limits of integration to be a's, where a is actually any number. But to keep things simple for the purposes of illustrating this today, I'm assuming little f of x is a continuous function that is decreasing in positive on some interval of this form. I don't know if you've seen this notation before. This is called the interval from 1 to infinity, including 1. As with set builder notation, it's the set of all real numbers x such that x is greater than or equal to 1. Everything to the right of 1, including 1 on a number line. Again, I could have picked some other number there to start with, call it a. I'm going to let ak be f of k. Those are going to be the terms of my series that I'm interested in. There's 2 parts. If this improper integral converges, then the series also converges. That's part A. On the other hand, part B, if the integral diverges, then the series diverges as well. We already used this last week for a P series. Last Friday. You had some homework problems where you used this. You have to, in order to officially apply it, you have to identify what f of x is. With a P series, that's a sub k. So according to the theorem setup, that's the same as f of k. So what is f of x? F of x would be 1 over x to the p. It's just a conceptual difference there. The letter really doesn't matter. Conceptually, I'm thinking of k as a positive integer and x as a positive real number. But you really don't have to change the variable name. We saw last Friday that the improper integral of 1 over x to the p from 1 to infinity converged when p was bigger than 1 and diverged when p was less than or equal to 1. We saw that last Friday. It is in the book back in chapter 7. We talked about it 5 or so weeks ago. It was in the section about the comparison test for improper integrals. It's right here, page 419. Actually, the 1 there is irrelevant. You could start at 2 or 3 or any positive number. And the 1 that's in the numerator is irrelevant. You could make that be any number. The important point is you're going off to infinity up there, and it's x to the p down there. Converges if p is bigger than 1 and diverges if p is less than or equal to 1. You can therefore use the integral test to prove exactly what you see here for p series. In the case where p is 1, that's also got an extra special name. It's called the harmonic series, which, because it fits the second case, that's the divergence case. However, sometimes when you need to apply the integral test, it's a harder problem. Oh, let's say we've got this series. Does this series converge or diverge? If we were going to try to use the integral test, we'd have to let f of x be x over e to the x. And we'd have to integrate that. Doesn't sound so easy, does it? Integrate x over e to the x. Have we ever done that before? I don't remember if I signed that exact problem, but we have talked about how to integrate such a thing in class when we wrote the function in a different form. Anybody think they know what I'm getting at? Let f of x be x over e to the x. There's a way to rewrite this function that makes it look easier to integrate. That's correct, x times e to the negative x. Dividing by e to the x is the same as multiplying by e to the negative x. And yeah, that looks easier to integrate. We've done examples like that before. In fact, it came up on the last test. And the problem about finding the mean of a exponential distribution where the variable represented the wait time to come into the intersection. Although we started the integral for that one at 0, it's going to be, if you want to be official with this theorem, we need to start the integral at 1, partially because it's stated that way, but partially because, more importantly though, because we do need to make sure our function is decreasing on this interval. And technically speaking, this function is not decreasing everywhere. I would be fine at this point, if you want to apply the integral test, for you to use your technology, your calculator, say, to confirm that this function is decreasing when x is greater than or equal to 1. You really should be able to confirm it by hand, though. It's really a calculus 1 problem. You'd want to differentiate this and see the derivative is always negative when x is greater than 1. Let's just graph it, though. X times e to the negative x, or if you prefer, x divided by e to the positive x. It does increase at first, but then once it reaches 1, it starts going down. Its critical point is at x equals 1, which you could verify by differentiation. Then f of x is continuous, positive, and decreasing when x is greater than or equal to 1. Actually, when x is negative, it's a negative valued function, but we don't care about that. We only care about when x is greater than or equal to 1. Does the improper integral of this thing converge? Let's calculate it. So on your homework, you might have to do calculations like this. The improper integral, which I should have initially written without a limit sign, is by definition of a limit, if the limit exists, as the upper limit of integration goes to infinity. And the way to do this integral by hand is integration by parts. U equals x, v prime equals e to the negative x. U prime would be 1, in other words, du would be dx. And to find v, you'd need to integrate v prime to get negative e to the negative x. It's a bit messy, but doable. U times v is x times negative e to the negative x. That's going to be what I put first. X going from 1 to b. Subtract the integral from 1 to b of v times u prime, the product of these two things. Two negatives are going to make a plus. I can put plus integral of e to the negative x. I really don't care what this limit equals. I just care about whether it converges or not. Plug in b. Subtract what you get when you plug in 1. Also do this integral, get negative e to the negative x, going from 0 to b, or 1 to b, excuse me. The limit as b goes to infinity. Oh, you know what? I forgot a minus sign. Let's see. There should be a minus sign here. I'll switch these around. I'll put the plus 1 over e to the negative 1 over e here, same as e to the negative 1. Minus b e to the negative b, minus, when you plug in the numbers here, you get e to the negative b, and minus e to the negative 1. Being a little sloppy here, this goes to 0 as b goes to infinity. This goes to 0 as b goes to infinity. Technically speaking, that needs proof, but I'd be fine if you just said it. Clearly does. You got a power function times an exponential decay. The exponential decay would win out to make this product go to 0. More officially, you could use L'Hopital's rule, but you do not have to do that for the assignment. That certainly goes to 0. You're left with e to the negative 1 minus negative e to the negative 1, which is positive 2e to the negative 1. But the important thing is that exists. The limit exists. It doesn't matter what it equals, just that it exists. The improper integral converges. Converges. Because now we can say, therefore, the series converges by the integral test. I'll write it in its original form. So important, again, that you get the terminology right and the notation right. I do not want to see conclusions here that do not have a summation sign. If you don't put the summation sign, you don't get it, okay? You don't get the point. You're missing the point. We're interested in whether the series converges or not the terms. I mean, yes, that's relevant. They got to go to 0, which they do. If the series is going to have a chance of converging. But yeah, they do. So you need something else. In this case, the integral test. Does it converge to 2 times e to the negative 1? No. What does it converge to? I don't know offhand. I think it can be figured out. I think it's a simple enough example that can be done. But I don't remember offhand what the answer would be. E over E minus 1 quantity squared, okay? It's not a geometric series. Okay, I do know how it was computed. It's not a geometric series, but it turns out, talking about this series here, it turns out it can be related to geometric series. Not going into details right now, we'll see that in a week or two. Can I clarify anything? Next test is like an old friend, comparison test. We had a comparison test for improper integrals in chapter 7. Now it's a comparison test for series. Ugh. The comparison test is super important, not just for particular series, but for the general theory of making sure everything can be proved. However, it's not much fun to use. Say it's kind of boring to use. You might also say, in simple examples like I'm about to show you, it's even kind of silly to use. Okay, I'm about to show you an example that when we go through it kind of feels silly. But what it is it's practice using the test, which is a worthwhile thing, to practice your deductive logic, even though it seems like silly deductive logic. It's worth getting the technical details right, if for nothing else than paying attention to detail and making sure you understand exactly what's going on. We'll consider a simple example. You can make really hard examples with this as well. Let K be a positive integer, that's a capital K. And suppose that these inequalities are true for all little k greater than or equal to capital K. What's capital K? It's just some positive integer. It doesn't matter what it is. In the theorem, at least. When you apply this, then it would be something particular. There's two statements. Statement A and statement B. Statement A says, if the original series, if the series of the BKs converges, then the series of the AKs converges as well. Think about it intuitively. If the series whose terms are bigger converges, it should make sense that the series whose terms are smaller also converges. The B's are bigger than the A's, at least when little k is big enough. On the other hand, if the series whose terms of the AKs diverges, then the series whose terms of the BKs also diverges. In other words, if the series whose terms are smaller diverges, then the series whose terms are bigger should also diverge. You're adding bigger numbers. Before I apply this, I need to inform you about a little bit of logic here that I taught earlier in the class period to the first section, but forgot to talk about with you guys. Look at the first statement. It's an if-then statement. It's called an implication. And we're saying it's true. And what that means is if you know the first part is true, the series of the BKs converges, where this thing is always assumed to be true as well. Then you can conclude with a guarantee that the series whose terms of the AKs also converges. It's a guarantee. Think of the phrase, the series converges, symbolically call it P. Why P? It's just what people do. P just represents that phrase, the series of the BKs converges. And think of this other phrase here, the series whose terms of the AKs converges, as another phrase, call it Q. If I make those shorthand notations, then I'm saying this implication, if P, then Q is true. It can be proved to be true. When you have a logical implication, if P, then Q, you can make other logical implications as well that are related to it. For example, you can make something called the converse. The converse says if Q, then P. Switch around the roles of Q and P. However, if this implication is true, which it is for this example, the converse may or may not be true. It depends. And in fact, in this example, it's not true. If you know the series whose terms of the AKs converges, it does not necessarily mean the series whose terms of the BKs converge. If the AKs are 1 over k squared, for example, P series with P equal to 2, which is bigger than 1, the series converges. And the BKs are all a bunch of 1s, 1 plus 1 plus 1 plus 1 plus 1, etc. Then that would be a situation where the series whose terms of the AKs converges, but the series whose terms of the BKs does not converge. That would be enough to disprove this converse. This is false. For this example, this is false. Another related statement is called the contrapositive of the original statement. This is the converse of the original statement. What's the contrapositive? You do switch around the P and the Q, but you put the word not in front of them. If not Q, then not P. That's the contrapositive statement. That, if the original statement is true, that is true. Because they really mean the same thing. Why? Why does this statement in red mean the same thing as this statement in blue? Think about it carefully. Suppose I know the statement in blue is true, which I do for this example. Why would this be true? Here's your argument. Well, if not P were false, in other words, if P were true, then Q would have been true, but it's not. Done. That probably went by too fast. Say it again. Pretend you know this is true, a true statement, and you're trying to prove this is a true statement. Assume Q is not true. In other words, assume not Q is true. Weird. Why does not P have to be true? Because if it were false, that would mean P is true, but P being true means Q is true, which means not Q is false, contradicting the fact that I assume that not Q is true. Oh, that's confusing. Why am I bringing this up? 2 reasons. If I take the contrapositive of part A, I get another true statement. If this series diverges, then this series diverges. Which is effectively part B. It is part B. Part B is the contrapositive of part A. If you prove A, you really prove B. And vice versa, in fact. It is also relevant for the very first page. With the divergence test, I forgot to talk about the first sentence. It says if this series converges, then the sequence of terms converges to 0. The second sentence really the contrapositive of the first. I think it's easier to think about proving the second sentence from the first with this example than is with the previous example in the abstract. Suppose you had a sequence of terms that did not go to zero. Why does this series diverge? If you assume the first sentence is true, you could argue like this, because if this series converged, then the first sentence would imply the AKs converge to zero, which they do not. Not the last time we'll talk about that, so if you feel confused, we'll come back to it. Anyway, coming back to the comparison test, what would be an example where you can apply this? Does, for example, this series converge or diverge? And I'm making it a fairly easy example. Again, I could make very hard examples. The authors of the textbook very much want you, and I agree with them, to first think about this intuitively. We did something similar with improper integrals. The general term, without a summation sign, acts like or behaves like 1 over k squared without a plus 1 when k is large. This is a vague statement. What does it mean to act like? What does it mean to say k is large? What does large mean anyway? We only have relative statements like greater than. You know, what is a big number? Is a million a big number? A billion? A Google? It depends on your perspective. Technically speaking, yeah, of course, a Google dollars is a lot of dollars. Even $1 billion or $1 million is a lot of dollars, and Google's more money than exists. But compared to infinity, a Google's small. Compared to a Googleplex, a Google's small. Compared to a Googleplex to the Googleplex power, a Googleplex is small. So this is vague, hand wavy. Why does it act like it? Because effectively the 1 doesn't matter, the plus 1, when k is large. Now we know the series whose terms are 1 over k squared converges. Therefore, we guess, is this a p series with p equal to 2? Therefore, guess that our series converges, and we try to prove it. By our series, I mean that one there. Question?
Because for every value of k,
Yeah, you're right. We could use the integral test. We-
I do the integral test. For every positive value of k, 1 over k squared is greater than 1 over k squared.
That's what we're talking about here. That's what we're doing. Yep. Here's the proof. Let AK be the smaller expression. 1 over k squared plus 1. Why is it smaller? Exactly what you said, David, I think. Because we're dividing by a bigger number. Let's first just mention AK is certainly greater than or equal to 0. Since k squared plus 1 is greater than or equal to k squared for all k greater than or equal to 1, AK, which is 1 over k squared plus 1, is less than or equal to 1 over k squared, which is BK for all k greater than or equal to 1. If you divide by a bigger number, you get a smaller number. At least when we're talking positive numbers. Okay, yes, I'll transfer this over. What have I done? I've confirmed that this condition is met. What's capital K? 1. It's this thing. That's the capital K. I'm mentioning that's the capital K. You don't have to mention that. What else should I do? I should confirm I know the series whose terms of the B case converges. The sum of the B case converges. We know that the series whose terms are 1 over K squared converges because it's a P series with P equal to 2, which is bigger than 1. Therefore, by the comparison test, the series whose terms are 1 over K squared plus 1 also converges. There's a proof. Not a ton of fun, right? Kind of boring, kind of silly. It feels silly, it's really not silly, I'm saying. It is worthwhile for you to go through these steps to learn how to construct logical arguments based on theorems. It's a worthwhile thing to do. I could make the problem a lot harder. I could make that a -1 instead of a +1, though if I did, I wouldn't want to start K at 1, I'd want to start at 2, so I'd want to avoid dividing by 0. Starting at 2 is irrelevant. It doesn't matter where you start the K. In fact, there's a theorem in the book that says the first finite number of terms don't matter as far as convergence or divergence. Or the finite number is any finite number of terms. Don't matter. So what's better more typically than the comparison test is something called the limit comparison test. Oh, limit sounds harder, but this is actually an easier test to use. Because you don't have to worry about inequalities. If you're going to be scared about limits or scared about inequalities in general in math, usually be more scared about inequalities. At least most people are when they get into math enough. Inequalities typically are harder to think about in most advanced examples situations. I mean, maybe that's overgeneralization, but limits in many particular examples are not as bad to deal with as you might imagine. I'm not saying they're easy, but they're often maybe not as bad as inequalities. Anyway, this is one example of such a situation. So does the series whose terms are starting at K equal to 2, 1 over K squared minus 1 converge or diverge? Notice the -1 instead of the +1. Use the limit comparison test. What does it say to do? Suppose you got series down here whose terms AK and BK are all positive. Also suppose that the limit of their ratio is some positive constant. The conclusion is these series either both converge or both diverge. If you know one converges, then the other converges. If you know one diverges, then the other diverges. The answer here is that it does converge, and the intuition is that the acting like idea still happens, except with the minus sign there. Whether you add 1 or subtract 1, it doesn't really matter with the behavior of the function when K is large. The answer is it does converge. Proof. We want to use the limit comparison test. Let AK be 1 over K squared minus 1 and BK be 1 over K squared. Notice these are both positive. For K greater than or equal to 2. Now the capital K in a sense is 2. It's not quite fitting this theorem because this says for all positive integers K, but I could have put a capital K in there and said for all positive integers little k greater than or equal to capital K and made it a slightly more general test. It's not a big deal. What do we need to compute? We need to compute this limit. The limit as k goes to infinity of ak divided by bk is the limit as k goes to infinity of 1 over k squared minus 1 all over 1 over k squared. I hope you know that that simplifies to k squared over k squared minus 1. And once again, we're in a situation where we've got a rational function of k, where the degree of the top and the bottom are the same. They're both 2. And so you'd look at the ratio of the coefficients of the highest powers. This limit is 1, which is a positive number. That's the c. Almost done. We know, once again, that the sum of the bk's converges because it's a p series with p equal to 2, which is bigger than 1. The conclusion is, therefore, the series of the AKs, starting at 2 even, which I have to start at 2. I can't start at 1 there, converges as well by the limit comparison test. So you don't have to worry about inequalities here other than just to say the A's and B's are positive. And for this example, that's much easier, because if you were going to try to use the ordinary comparison test here, you could not use that for the BKs. You'd have to modify it some way. It's doable. You could maybe modify it by doing 2 over k squared instead of 1 over k squared. But then you'd have to verify that the 2 really works. And the A's are still always less than the B's if you put a 2 up there. I believe it does work, but you'd have to make a modification that makes it trickier. So the limit comparison test, you don't have to worry about inequalities. Hang on here, 7 minutes left of class. We still need to keep going. Take a breath. Another theorem. Absolute convergence implies convergence. We're interested in knowing whether a series whose terms are AK converges or not. If you happen to look at this series and see it converges, then the conclusion is the original series converges. If you look at the series whose terms are the absolute values of the AKs, and if you know somehow that that converges, this theorem guarantees the original series converges. What's a good example of that? Let's consider our old friend, the P series with P equal to 2, except let's make the numerator -1 to the k plus 1. So that the series alternates in sign, plus, minus, plus, minus. Does this series converge? All the tests we've done so far cannot be used. The divergence test does not apply because these terms do go to 0 as k goes to infinity. It's not geometric. Can't use the comparison test or the limit comparison test because the terms need to be positive in those cases. Can't use the integral test because how would you integrate -1 to the x plus 1 over x squared? And it's a problem anyway, since such a function is not continuous or decreasing. Can't use any test that we have so far, but we can use this new test. This absolute convergence implies convergence, because what we can do, these are the AKs here, is we can consider the corresponding series whose terms are the absolute values of the AKs, which gets rid of the -1 to the k plus 1. And it becomes the P series with P equal to 2, which we know converges because 2 is bigger than 1. This converges. Therefore, the original series converges. By original series, I mean that one up there converges by this new theorem here. Absolute convergence implies convergence. By absolute convergence, I mean the convergence of this series. Maybe not the best name because it could be confusing, but it's a theorem. It was at this point in the class with the first section that we had to end, but you guys have 4 minutes still. I told the other class to read examples of the ratio test, but I think we have enough time to do one example here. And I'll share the video with them. Ratio test. Let this be a series with non-zero terms, meaning they could be positive or negative, but non-zero. And suppose the limit of this ratio exists for some number L. This is a different ratio than the limit comparison test. We're just have one series here. If L is less than 1, then the series converges. In fact, absolutely. If L is greater than 1, then the series diverges. And the book states it as if L is 1, then this test gives no information. That's really more of a note, like I'm saying here. Here's our last example of the day. Does this series converge or diverge? Notice it involves an exponential function, 2 to the k, and a factorial function, k factorial. The ratio test is often useful with factorials, as you have here. What would the first few terms be here? When k is 1, it would be 2 to the first over 1 factorial. When k is 2, it would be 2 squared over 2 factorial, then 2 cubed over 3 factorial, 2 to the 4th over 4 factorial, etc. Both the numerator and denominator here are getting big. So it's not clear whether this is really going to converge or not. 16/24 is 2/3. That fraction could be reduced. It's not clear. Will this converge or not? Does this converge or diverge? The best thing to try is the ratio test. The terms are already positive. I will write the absolute value signs here, but because those terms are positive, I really don't need them. But sometimes you do need them. Here we don't. What is AK plus 1? This is AK. What's AK plus 1? Just substitute. Replace k with k plus 1. In both spots. 2 to the k plus 1 over k plus 1 factorial. That's a sub k plus 1. What's AK? It's 2 to the k divided by k factorial. I'm dividing two fractions. I can multiply by the reciprocal of the bottom. It's also a handy thing to write 2 to the k plus 1 as 2 to the k times 2, and write k plus 1 factorial as k plus 1 times 1 k factorial. Now, this is making me realize some of you may not know what the factorial function is. I'm going to let you look it up. Let me just quickly finish this. You can do some cancellation. The 2 to the k's cancel. 1 of the k factorials cancels. And you're left with the limit as k goes to infinity of 2 over k plus 1. That limit does exist. It equals 0. That's the L. That's less than 1. Therefore, the series converges. Even though both the top and the bottom are both getting big pretty quickly, the bottom wins out, making the fractions go to 0 quick enough to make this converge. This converges. Oops, sorry. There's the end. Have a good day.